One way to answer it is you can compute a confidence interval. So you cannot compute a range for the generalization error. You cannot say it is guaranteed to be smaller than this number and higher than this number, but you can compute a confidence interval. So you can say with a certain probability, say with a probability 95%, the future error will be in a certain error bound around the testing error that you have computed. So, and what that would mean is basically, if you think of all possible future sets that could come tomorrow, 95% of them will fall inside the confidence interval, and 5% will fall outside. So that's the best you can do. So how do we compute a confidence interval? So we start with our testing error, that's e-test. We know it's an unbiased estimate, assuming our testing set was sampled in a representative way. It's an unbiased estimate of the true error rate. Now, what is the true error rate? The true error rate, that's the probability. Remember, we're doing binary classification. So the true error rate is the probability that our system misclassifies a randomly given input. So it got a positive and it predicted a negative. That's the definition of E. So what if we take a random subset of n instances that comes tomorrow, and E is the true error rate? How many instances would be misclassified? And that's simple to estimate because our classifier operates independently for each one of the instances, right? So the mistake that it makes on one instance doesn't affect the mistakes on other instances. So the question of how many will it misclassify, it's similar to the question of flipping a coin, right? So I have a coin that, say, comes up heads 25% of the time and tails 75% of the time, and I flip it 100 times. So how many heads will I have? Well, I'll have 25 heads. And that's because that follows a binomial distribution, right? So n is the number of flips that I do, E is the probability that I get a head, or n is the number of instances that I'm classifying, and E is the probability that I misclassify any given instance. So the total number of misclassified instances is going to be around NE, but it can vary depending on the different sets that I get. So over all of those sets, the average number of misclassified is going to be NE, and the variance in the number of misclassified is going to be NE1 minus E. So again, what I'm doing is I'm considering different sets of 100 items that could come in the future. So over those sets, the mean number of misclassified is NE, and the variance is NE1 minus E. And by the way, our test set is just one of such sets. So that's the number of misclassified. Now, the future error rate, that's just the number of misclassified divided by the total number in the future set that we're trying to classify. So if the number of misclassified follows a binomial distribution, then the error rate is going to follow a Gaussian distribution. And it's going to have mean E, which is as you would expect it, right? So the expected future error rate is just the true error rate, E. And the variance is going to be E1 minus E divided by N. Right? Why it's divided by N? Remember, here the variance was N, and we're transforming the variable, we're dividing it by N, and the variance you divide by the square of the constant. So it's going to be E1 minus E over N. So if you try to draw it, basically that's what you're looking at. So over all future test sets that could come tomorrow, the errors will follow a Gaussian distribution. So on average, the error is going to be E. That's going to be the mean of that Gaussian, so 25% in our case. And then some will have a smaller error, some will have a larger error, and the variance, or the standard deviation, how fat this Gaussian is given by that. E1 minus E over N. That's just the standard deviation of the Gaussian. So you have a picture of what the future error rates will look like. Just that curve. Now, if your goal is not just to get that picture, if your goal is to compute a confidence interval, you're asking a question: how how wide should I pick a confidence interval such that 95% of all future test sets land inside that interval and only 5% land outside. And you can compute that fairly easily. So for a Gaussian, for example, you know that if you take the mean and go one standard deviation left and right, then that will capture about 2/3 of the mass under the Gaussian. So 2/3 of the future test sets will be the mean plus or minus the square root of this, the square root of the variance. But that's 2/3. So what if you wanted to take that 2/3 and expand it out to 95%? That's simple as well. You just need to look up how many standard deviations do I need to step left and right to capture 95% of the data. And that's just the inverse of the Gaussian cumulative distribution function. So it's a hairy formula, but it's easy enough to implement. So here are some examples. So if we had if our n was 100 instances, so we're looking at future test sets of 100 instances each, and we want a 95% confidence interval, and our error rate is 25%. So that's the true error rate, and remember, our testing error rate is an unbiased estimate of that. So that's 25%. So in that case, the standard, that's the mean of the Gaussian, so it's going to be around 25%. The standard deviation is 0.043, and the way I'm computing it is I'm just taking E, which is 0.25, times 1 minus C, 0.75, divided by N, which is the total number of entries in the test set, taking square root of that, get 0.043. Now, to get a 95% confidence interval, I need to get almost two standard deviations left and right. So the confidence interval overall would be that. It would be 25% plus or minus 8%. So that would be my estimate of the future error rate, given that I have a testing set with 100 examples and I get a testing error of 25%, and I want a 95% confidence. If I wanted a higher confidence, not surprisingly, higher confidence means more of the future test sets have to fall within the range, so I have to expand the range. So it's going to be more standard deviations to the left and the right of the mean. It's 0.25 plus or minus 11%. Right? So that's if I wanted a 99% confidence interval. Now, if I was happy with 95%, but I had 100 times more data, my confidence interval would actually shrink very substantially. So it would still be, the mean would still be 25%, right? That's my expected misclassification, but now I'm much more confident about that number. So previously I had plus or minus 8%, now I have plus or minus 0.8%. And there's an interesting, very straightforward relationship between the number of instances in your test set and the size of the confidence interval. Because remember, the confidence interval, it's really just, so this is a constant that depends on p, and so you can ignore it safely. The mean never changes. The only thing that changes is this part, which is the standard deviation. And the standard deviation depends on n, right? So the variance, again, you can't affect that. That's determined by your error rate on the test set. That's just 2 times 1 easy. But you're dividing by n, which is the number of elements in your test set. And then you're taking a square root. So if you have 100 times more data in your test set, your confidence interval is going to shrink by a square root of 100, so by a factor of 10. And you see that there, right? So it shrinks from 8% to 0.8% when the data grows from 100 to 10,000 examples.